In this video, we will be looking at section 3.1, which covers power functions and polynomial functions. We're going to start off with some definitions. A power function is a function that can be represented in the form f of x equals x to the p power, where the base, in this case x, is a variable and the exponent p is a number. So we just have x raised to a power. What we're going to be focusing on a good majority of this section is the long run behavior. The long run behavior is the behavior of the graph of a function as the input takes on large negative values, meaning as x goes to negative infinity, what happens to the y value? And large positive values, meaning as x goes to positive infinity, what happens to the y value? I printed out what the slide actually looks like, but in black and white it's not super great. So I am going to switch us over to Desmos so we can see a little bit better what's going on. So right now we are looking at the graph of x squared. So we are looking at even power functions right now. It looks like a parabola, everything's normal. Let's add in x to the fourth. Well, it looks a lot like x squared, but it kind of flattens out at the bottom here. So it's getting to be closer to the x-axis for a little bit longer span here. What if we add x to the sixth? Kind of the same thing. We come down, get flat, go back up again. And x to the eighth, same thing. So it looks like all of these even powers, if I zoom out we can see kind of the larger scale, as x goes towards negative infinity, so as we go to the left on this graph, we are going up forever. So as x goes to negative infinity, our y value goes to positive infinity. The same on the right-hand side. So no matter whether you go to the left or the right, our y values are going towards infinity. We noticed that as the power of x gets higher, our flat area gets wider. Something else that's interesting to note is all of our graphs go through the point -1, 1 and 1, 1, as well as 0, 0, the origin. So that's what even functions look like, even power functions. Let's take a look at odd power functions. So we start with y equals x because that's x to the first power. That's something that we've seen 1,000 times. But let's see as the powers of x get bigger, what happens. So x cubed, we're coming up, we get flat and we continue up. X to the fifth, we still have that same shape where we come up, get flat, and go back up, but our flat area is a little bit longer. X to the seventh, same deal. We're still getting a longer flat part, but if we look on the big scale of things, we always start in the negatives for y and go towards the positives. So as x goes towards negative infinity, our y values are also going towards negative infinity. So we're starting with y values in the negative infinity, and as we go towards the right, as our x increases, our y values are going towards positive infinity. Kind of like how we had common points among all of the even power functions, we have common points between the odd power functions. So all of our odd power functions are going through the point -1, -1, 0, 0, and 1, 1. So that's some interesting notes to take into consideration. So let's see if we can figure out the long run behavior of some power functions. First up, we have f of x equals -x to the fifth. So we saw x to the fifth. That is an odd power function. And odd power functions do something like this. But notice there is a negative out front. From our learning, from our knowledge of function transformations, what does that negative out front do? A negative out front is a vertical reflection. So if I were to flip this graph vertically, then it would look something like this. So this is our rough sketch of x to the 5th power. This is our rough sketch of negative x to the 5th power. So for our long run behavior, we would say as x goes towards negative infinity, our function values f of x go towards, so as we go to the left, our function values, our y values are going up, so our function values go towards positive infinity. As x goes towards positive infinity, so as we go to the right, what happens to our function values? As we go to the right, we're going down, so f of x goes towards negative infinity. Next up, we're looking at g of x equals x to the 12th. We didn't actually see the graph of x to the 12th, but we did see a pattern between our even-powered functions, and they all kind of sort of looked like this. Kind of had that flat part in the middle. There aren't any negatives, so we're not flipping this around at all. So this is our rough sketch of x to the 12th. So we would say as x goes towards negative infinity, g of x, our function values, as we go to the left, we're going up. So we're going towards y values, going towards infinity. As x goes towards positive infinity, g of x also goes towards positive infinity because they go up on both sides. Next up, we're going to look at h of x, which is negative x to the 24th. So again, we have that even power function. So if we were to graph x to the 24th, it would look something like that. But kind of like the first example, we have a negative out front. That negative gives us a vertical reflection. So if we reflect it, it's going to look something like that. And that's going to look like a rough sketch of negative x to the 24th. So as x goes towards negative infinity, the function values h of x goes towards negative infinity because we're going down. And then as x goes towards positive infinity, our h of x values are still going to go towards negative infinity because they're also down. One thing I would like to point out here is that with even power functions, our function values go the same direction. So either they're both up or both down. Whereas for our odd power functions, our function values are going opposite directions. So one goes towards positive infinity and the other goes towards negative infinity. So that's kind of an interesting little thought there. We're going to look at some more definitions so that we can look at polynomials a little bit more closely. So starting off with the definition of a polynomial in general, it is a function that can be written as f of x equals a sub 0 plus a sub 1x plus a sub 2x squared all the way up to a sub n x to the n. So what we're noticing is all our powers of x are integers. In fact, they're positive integers. Usually we write these in the opposite order, so we would start with the highest power on x and write it down to our constant. Coefficients are the numbers out front. They're the a sub I constants multiplied by the power functions. So you'll notice that this polynomial is just a bunch of power functions added together with coefficients. A term is any one piece of the sum of a polynomial. So we have the term a0, we have the term a sub 1x, we have the term a sub 2x squared. If you see a plus or a minus sign, that starts a new term. The degree of the polynomial is going to be the highest power of the variable that occurs in the polynomial. So it's going to be the highest power on x that we see. Our leading term is going to be the term with the highest degree. So when we find the highest power on x, that full term is going to be our leading term. And then the coefficient on that term is going to be our leading coefficient. So let's see if we can put these definitions to use. We are going to identify the degree, the leading term, and the leading coefficient for the following polynomials. First up, we have f of x equals 6 plus 2x plus 7x cubed minus 9x squared. So let's start with the degree. The degree of a polynomial is the highest power on x. The 6 doesn't have an x. 2x just means 2x to the first power. We have an x to the third power and an x squared. So it looks like the highest power on x is 3. Next up, we want to find the leading term. That's the entire term that has the highest degree. So we got that degree from this term here, which is a positive 7x cubed. And then our leading coefficient is just the coefficient on that leading term. So our leading term was the 7x cubed. The constant that's being multiplied by x cubed is a positive 7. So our leading coefficient is 7. Next up, we're going to look at g of r equals r to the 5th minus 4r to the 4th plus 7r squared minus 2. We'll start with the degree. So we're looking for the highest power on our variable. In this case, our input variable is r. So I'm looking for the highest power on r. It looks like the highest power we have is a 5. Our leading term is the entire term with that degree. And it looks like it's just the r to the 5th. And then our leading coefficient is going to be the number multiplied by the power function in our leading term, or the coefficient on this leading term. Since I don't see one, I have to remember that there's an invisible 1 out front. So our leading coefficient is going to be 1. I would like to point something out before we go on. These terms always start with the sign in front of them. So our first term is r to the 5th. Our second term is negative 4r to the 4th. Our next term is a positive 7r squared. And our next term is a negative 2. So the coefficient on this r to the 4th term is a negative 4. So just make sure that the sign that comes before the term stays with that term. Next up, we're going to look at the long-run behavior of polynomials. So for any polynomial, the long-run behavior of the polynomial will match the long-run behavior of the leading term. So what that's saying is, if we are looking at a polynomial and we want to know the long-run behavior, we only care about the leading term. The long-run behavior is going to match that. So we want to describe the long-term behavior of f of t equals t to the 4th plus 3t squared minus 3. So what is our leading term here? The leading term is the term with the highest power on the variable. So that's going to be our t to the 4th. The long-term behavior, or the long-run behavior of this polynomial, is going to match the long-run behavior of t to the 4th. Well, when we had a 4th power, our graph looked something like that. So that kind of represents t to the 4th. So that means as t goes towards negative infinity, f of t, our function values, go towards, as we go to the left, we're going up. So our function values go toward infinity. As t goes towards positive infinity, our function values f of t also go towards infinity, because as we go to the right, we go up. Now we're going to look at intercepts and turning points. So a polynomial of degree n will have at most n horizontal intercepts. So for example, if we have a polynomial of degree 3, meaning we have an x cubed, but nothing higher than that, then we can have at most 3 horizontal intercepts, 3 x intercepts. We can't have more intercepts than our degree. If our n value is odd, so if our degree is odd, there's going to be at least one horizontal intercept every single time. And at most, there's going to be n minus 1 turning points. And you're like, what's a turning point? If we have a polynomial function, if I could draw, that'd be great. A turning point is where you switch from increasing to decreasing or decreasing to increasing. So that's a turning point, that's a turning point, that's a turning point. Somewhere in here there's a turning point. So it's just where we switch from going up to going down or vice versa. So we're going to take a look at two graphs and see what we can figure out about them. So let's zoom in and see what we've got. So let's take a look at our horizontal or our x-intercepts. We have 1, 2, 3, 4, 5, 6, 7. So we have 7 intercepts. That means our degree is at least 7. Our degree could be more than 7, but it can't be less because we have 7 of those horizontal intercepts. There's something else we know about this graph based on its long-run behavior. Notice that as we go towards the left on our graph, as x goes towards negative infinity, then our y values, our function values, go towards negative infinity. And as we go to the right, our function values goes towards positive infinity. They're not the same, they're different. So that means we know this is an odd degree function. So we are positive that the degree is 7 or higher, and it's also an odd degree. One more thing we can notice is the fact that as we go to the left, we go towards negative infinity, and the right, we go towards positive infinity. That's like just our regular odd power functions. So our leading coefficient must be positive because we didn't flip the graph. It still goes towards negative infinity on the left and towards positive infinity on the right. So we know the leading coefficient is positive. Let's take a look at this other guy. So we have 1, 2 horizontal intercepts. So we have at least a degree of 2. Wait a minute. That slide before this said that a graph has at most n minus 1 turning points. Look at how many turning points there are here. We have 1, 2, 3 turning points. That means we have at least a degree of 4 because we have to add 1 to get back to n. This is at least degree 4. If we look at the long-run behavior, we're going the same direction on both sides, so we know this is an even degree. They're both going towards negative infinity. Our normal even power functions both go towards positive infinity, so we have flipped it vertically. That means our leading coefficient is going to be negative this time because we have to flip that graph over. take some time to practice these because they're going to give us a lot of information about the functions we're looking at in the future.